Hello, I'm Paul and welcome to RGD Paranormal Files. Please hit like and subscribe. Thank you. Time travel is commonly defined with David Lewis's definition. An object time travels if and only if the difference between its departure and arrival times as measured in the surrounding world does not equal the duration of the journey undergone by the object. For example, Jane is a time traveler if she travels away from home in her spaceship for 1 hour, as measured by her own clock on the ship, but travels 2 hours, as measured by the clock back home, assuming both clocks are functioning properly. Before the 20th century, scientists and philosophers rarely investigated time travel, but now it is an exciting and deeply studied topic. There are investigations into travel to the future and travel to the past, although travel to the past is more problematical and receives more attention. There are also investigations of the logical possibility of time travel, the physical possibility of time travel, and the technological practicality of time travel. The most attention is paid to time travel that is consistent with current physical theory, such as Einstein's general theory of relativity. In science, different models of the cosmos and the laws of nature governing the universe imply different possibilities for time travel. So theories about time travel have changed radically, as the dominant cosmological theories have evolved from classical Newtonian conceptions to modern relativistic and quantum mechanical conceptions. Philosophers were quick to note some of the implications of the new physics for venerable issues in metaphysics, the nature of time, causation, and personal identity, to name just a few. The subject continues to produce a fruitful cross-fertilization of ideas between scientists and philosophers, as theorists in both fields struggle to resolve confounding paradoxes that emerge when time travel is pondered seriously. This article discusses both the scientific and philosophical issues relevant to time travel. Time travel stories have been a staple of the science fiction genre for the past century. Good science fiction stories often pay homage to the fundamentals of scientific knowledge of the time. Thus, we see time travel stories of the variety typified by H.G. Wells as set within the context of a Newtonian universe, a three-dimensional Euclidean spatial manifold that changes along an inexorable arrow of time. By the early to mid-20th century, time travel stories evolved to take into account the features of an Einsteinian universe, a four-dimensional space-time continuum that curves, and in which time has the character of a spatial dimension. That is, there can be local variations or warps. More recently, time travel stories have incorporated features of quantum theory. Phenomena such as superposition and entanglement suggest the possibility of parallel or many universes, many minds, or many histories. Indeed, the sometimes counterintuitive principles and effects of quantum theory have invigorated time travel stories. Bizarre phenomena like negative energy density, the Casimir effect, lend their strangeness to the already odd character of time travel stories. In this article, we make a distinction between time travel stories that might be possible within the canon of known physical laws and those stories that contravene or go beyond known laws. The former type of stories, which we shall call natural time travel, exploit the features or natural topology of space-time regions. Natural time travel tends to severely constrain the activities of a time traveler and entails immense technological challenges. The latter type of stories, which we shall call Wellesian time travel, enable the time traveler more freedom and simplify the technological challenges, but at the expense of the physics. For example, in H.G. Wells' story, the narrator is a time traveler who constructs a machine that transports him through time. The time traveler's journey, as he experiences it, occurs over some non-zero duration of time. Also, the journey is through some different non-zero duration of time in the world. It is the latter condition that distinguishes the natural time travel story from the Wellesian time travel story. Our laws of physics do not allow travel through a non-zero duration of time in the world, in a sense that will be made clearer below. Wellesian time travel stories are mortgaged on our hope or presumption that more fundamental laws of nature are yet to be discovered beyond the current horizon of scientific knowledge. Natural time travel stories can be analyzed for consistency with known physics, while Wellesian time travel stories can be analyzed for consistency with logic. Finally, time travel stories implicate themselves in a constellation of common philosophical problems. Among these philosophically related issues we will address in this article are the metaphysics of time, causality, and personal identity. What is time travel? One standard definition is that of David Lewis's: an object time travels if and only if the difference between its departure and arrival times in the surrounding world does not equal the duration of the journey undergone by the object. This definition applies to both natural and Wellesian time travel. For example, Jane might be a time traveler if she travels for 1 hour but arrives 2 hours later in the future, or 2 hours earlier in the past. In both types of time travel, the times experienced by a time traveler are different from the time undergone by their surrounding world. But what do we mean by the time in time travel? And what do we mean by travel in time travel? As the definition for time travel presently stands, we need to clarify what we mean by the word time. See the next section. While philosophical analysis of time travel has attended mostly to the difficult issue of time, might there also be vagueness in the word travel? Our use of the word travel implies two places, an origin and a destination. I'm going to Morocco means I'm departing from my origination point here, and I plan to arrive eventually in Morocco. But when we are speaking of time travel, where exactly does a time traveler go? The time of origin is plain enough. The time of the time traveler and the time traveler's surrounding world coincide at the beginning of the journey. But where does the time traveler arrive? Are we equivocating in our use of the word travel by simply substituting a when for a where? In truth, how do we conceive of a when as a place, a locale, or a region? Different scientific ontologies result in different ideas of what travel through time might be like. Also, different metaphysical concepts of time result in different ideas of what kinds of time travel are possible. It is to the issue of time and philosophy that we now turn. How is time related to existence? Philosophy offers three primary answers to this metaphysical question: eternalism, possibilism, and presentism. The names of these views indicate the ontological status given to time. The eternalist thinks that time, correctly understood, is a fourth dimension, essentially constitutive of reality together with space. All times past, present, and future are actual times, just like all points distributed in space are actual points in space. One cannot privilege any one moment in the dimension of time as more real than any other moment, just like one cannot privilege any point in space as more real than any other point. The universe is thus a space-time block, a view that has philosophical roots at least as far back as Parmenides. Everything is one, the appearance of things coming to be and ceasing to be, of time passing or flowing, is simply phenomenal, not real. Objects from the past and future have equal ontological status with present objects. Thus, a presently extinct individual dodo bird exists as equably as a presently existing individual house finch, and the dodo bird and the house finch exist as equably as an individual baby sparrow hatched next Saturday. Whether or not the dodo bird and the baby sparrow are present is irrelevant ontologically. They simply aren't in our space-time region right now. The physicist typically views the relation of time to existence in the way that the eternalist does. The life of an object in the universe can be properly shown as this diagram shows the spatial movement in one dimension of an object through time. The standard depiction of an object's space-time world line in special relativity, the Minkowski diagram, see below, privileges this block view of the universe. Many Wellesian time travel stories assume the standpoint of eternalism. For example, in Wells's The Time Machine, the narrator, the time traveler, explains, "There is no difference between time and any of the three dimensions of space, except that our consciousness moves along it." Eternalism fits easily into the metaphysics of time travel. The second view is possibilism, also known as the growing block or growing universe view. The possibilist thinks that the eternalist's picture of the universe is correct except for the status of the future. The past and the present are fixed and actual. The future is only possible. Or more precisely, the future of an object holds the possibility of many different world lines, only one of which will become actual for the object. If eternalism seems overly deterministic, eliminating indeterminacies and human free choice, then possibilism seems to retain some indeterminacy and free choice, at least as far as the future is concerned. For the possibilist, the present takes on a special significance that it does not have for the eternalist. The life of an object, according to possibilism, might be shown as this diagram shows that the object's world line is not yet fixed or complete. It should be pointed out that the necessity of illustrating the time axis with a beginning and end should not be construed as an implicit claim that time itself has a beginning and end. Some Wellesian time travel stories make use of possibilism. Stories like Back to the Future and Terminator suggest that we can change the outcome of historical events in our world, including our own personal future, through time travel. The many different possible histories of an object introduce other philosophical problems of causation and personal identity, issues that we will consider in greater depth in later sections of the article. The third view is presentism. The presentist thinks that only temporally present objects are real. Whatever is, exists now. The past was but exists no longer. The future will be but does not exist yet. Objects are scattered throughout space, but they are not scattered throughout time. Presentists do not think that time is a dimension in the same sense as the three spatial dimensions. They say the block universe view of the eternalist and the intermediate view of the possibilist gets the metaphysics of time wrong. If eternalism has its philosophical roots in Parmenides, then presentism can be understood as having its philosophical roots in Heraclitus. Presently existing things are the only actuality, and only what is now is real. Each now is unique. You cannot step twice into the same river, for fresh waters are ever flowing in upon you. The life of an object, according to presentism, might be shown as many presentists account for the continuity of time, the time-like connection of one moment to the next moment, by appealing to the present intrinsic properties of the world, Bigelow. To fully describe some of these present intrinsic properties of the world, you need past and future tense truths to supervene on those properties. For example, in ordinary language, we might make the claim that George Washington camped at Valley Forge. This sentence has an implicit claim to a timeless truth. That is, it was true 500 years ago. It was true when it was happening. It is true now, and it will be true next month. But according to presentism, only presently existing things are real. Thus, the proper way to understand the truth of this sentence is to translate it into a more primitive form, where the tense is captured by an operator. So in our example, the truth of the sentence supervenes on the present, according to the formulation, was George Washington camps at Valley Forge. In this way, Presentists can describe events in the past and future as truths that supervene on the present. It is the basis for their account of persistence through time and issues like causality and personal identity. Since the use of the term time in our definition of time travel remains ambiguous, we may further distinguish external or physical time from personal or inner time. Again, following Lewis. In the ordinary world, external time and one's personal time coincide with one another. In the world of the time traveler, they do not. So with these two senses of time, we may further clarify time travel to occur. When the duration of the journey, according to the personal time of the time traveler, does not equal the duration of the journey in external time. Most, but not all, philosophy of time concerns external time. For the purpose of natural time travel, we need to examine the scientific understanding of external time and how it has changed. Newton argued that space, time, and motion were absolute. That is, that the entire universe was a single uniform inertial frame, and that time passed equably throughout it according to an eternally fixed, immutable, and inexorable rate without relation to anything external. Natural time travel in the Newtonian universe is impossible. There are no attributes or topography of space or time that can be exploited for natural time travel stories. Only time travel stories that exceed the bounds of Newtonian physics are possible, and scenarios described by some Wellesian time travel stories are examples of such unscientific time travel. Several philosophers and scientists objected to the notion of absolute space, time, and motion, most notably Leibniz, Berkeley, and Mach. Mach rejected Newton's implication that there was anything substantive about time. It is utterly beyond our power to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the changes of things. For Mach, change was more fundamental than the concept of time. We talk about time passing, but what we're really noticing is that things move and change around us. We find it convenient to talk as if there were some underlying flowing substance, like the water of a river, that carries these changes along with it. We abstract time to have a standard measuring tool by which we can quantify change. These views of Mach's were influential for the young Albert Einstein. In 1905, Einstein published his famous paper on special relativity. This theory began the transformation of our understanding of space, time, and motion. The theory of special relativity has two defining principles: the principle of relativity and the invariance of the speed of light. Briefly, the principle of relativity states that the laws of physics are the same for any inertial observer. An observer is an inertial observer if the observer's trajectory has a constant velocity and therefore is not under the influence of any force. The second principle is the invariance of the speed of light. All inertial observers measure the speed c of light in a vacuum as 3 times 10 to the 8th meters per second, regardless of their velocities relative to one another. This principle was implied in Maxwell's equations of electromagnetism, and the constancy of c was verified by the Michelson-Morley interferometer experiment. This second principle profoundly affected the model of the cosmos. The constancy of c was inconsistent with Newtonian physics. The invariance of the speed of light according to special relativity replaces the invariance of time and distance in the Newtonian universe. Intervals of space, like length, and intervals of time, and hence motion, are no longer absolute quantities. Instead of speaking of an object in a particular position independently of a particular time, we now speak of an event in which position and time are inseparable. We can relate two events with a new quantity, the space-time interval. For any pair of events, a space-time interval is an absolute quantity, that is, has the same value for all inertial observers. To visualize this new quantity, one constructs space-time diagrams, Minkowski diagrams, in which an event is defined by its spatial position and its time. What are the consequences of special relativity for time travel? First, we lose the common sense meaning of simultaneity. For example, the same event happens at two different times if one observer's inertial frame is stationary relative to another observer's inertial frame moving at some velocity. Furthermore, an observer in the stationary inertial frame may determine two events to have happened simultaneously, but an observer in the second moving inertial frame would see the same two events happening at different times. Thus, there is no universal or absolute external time. We can only speak of external time within one's own frame of reference. The lack of simultaneity across frames of reference means that we might experience the phenomenon of time dilation. If your frame of reference is moving at some fraction of the speed of light, your external time passes more slowly than the external time in a frame of reference that is stationary relative to yours. If we imagine that someone in the stationary frame of reference could peek at a clock in your frame of reference, they would see your clock run very slowly. So, in special relativity, we can find a kind of natural time travel. An example of special relativity time travel is of an astronaut who travels some distance in the universe at a velocity near the speed of light. The astronaut's personal time elapses at the same rate it always has. He travels to his destination and then returns home to find that external time has passed there quite differently. Everyone he knew has aged more than he, or perhaps has even been dead for hundreds or thousands of years. Such stories are physically consistent with the Einsteinian universe of special relativity, but of course they remain technologically beyond our present capability. Nevertheless, they are an example of a natural time travel story adhering to the known laws of physics, which do not require exceptions to fundamental scientific principles, like the invariant and inviolable speed of light. But as a time travel story, they require that the time traveler also be an ordinary traveler too, that is, that he travels some distance through space at extraordinary speeds. Furthermore, this sort of natural time traveler can only time travel into the future. Conversely, from the perspective of those in the originating frame of reference, when the astronaut returns, they witness the effects of time travel to the past, perhaps because they have a person present among them who was alive in their distant past. So natural time travel, according to special relativity, is perhaps too limited for what we normally mean by time travel, since it requires considerable spatial travel in order to work. In addition, there are other limitations, not least of which is mass-energy equivalence. This principle was published by Einstein in his second paper of 1905, entitled "Does the Inertia of a Body Depend Upon Its Energy Content?" Mass-energy equivalence was implied by certain consequences of special relativity. Mass-energy equivalence is expressed by the famous formula, E equals mc squared. It means that there is an energy equivalent to the mass of a particle at rest. When we harmonize mass-energy equivalence with the conservation law of energy, we find that if a mass ceases to exist, its equivalent amount of energy must appear in some form. Mass is interchangeable with energy. Now only massless objects, like photons, can actually move at the speed of light. They have kinetic energy, but no mass energy. Indeed, all objects with mass at rest, like people and spaceships, cannot in principle attain the speed of light. They would require an infinite amount of energy. In special relativity, all inertial frames are equivalent, and while this is a useful approximation, it does not yet suggest how inertial frames are to be explained. Mach had stated that the distribution of matter determines space and time, but how? This was the question answered by Einstein in his theory of general relativity in 1916. Special relativity is actually a subset of general relativity. General relativity takes into account accelerating frames of reference, that is, non-inertial frames, and thus the phenomenon of gravity. The topography of space-time is created by the distribution of mass. Space-time is dynamic, it curves, and matter tells a region of space-time how to curve. Likewise, the resultant geometry of a space-time region determines the motion of matter in it. The fundamental principle in general relativity is the equivalence principle, which states that gravity and acceleration are two names designating the same phenomenon. If you are accelerating upwards at a rate g in an elevator located in a region of space-time without a gravitational field, the force you would feel and the motion of objects in the elevator with you would be indistinguishable from an elevator that is stationary within a downward uniform gravitational field of magnitude g. To be more precise, there is no force of gravity. When we observe astronauts who are in orbit over the Earth, it is not true to say that they are in an environment with no gravity. Rather, they are in free fall within the Earth's gravitational field. They are in a local inertial frame and thus do not feel the weight of their own mass. One curious effect of general relativity is that light bends when it travels near objects. This may seem strange when we remember that light has no mass. How can light be affected by gravity? Light always travels in straight lines. Light bends because the geometry of space-time is non-Euclidean in the vicinity of any mass. The curved path of light around a massive body is only apparent. It is simply traveling a geodesic straight line. If we draw the path of an airplane traveling the shortest international route in only 2 dimensions, like on a flat map, the path appears curved. However, because the Earth itself is curved and not flat, the shortest distance, a straight line, must always follow a geodesic path. Light travels along the straight path through the various contours of space-time. Another curious effect of general relativity is that gravity affects time. Imagine a uniformly accelerating frame, like a rocket during an engine burn. General relativity predicts that depending on one's location in the rocket, one will measure time differently. To an observer at the bottom or back of the rocket, a clock at the top or front of the rocket will appear to run faster. According to the principle of equivalence, then, a clock at sea level on the Earth runs a little slower than a clock at the top of Mount Everest because the strength of the field is weaker the further you are from the center of mass. Are natural time travel stories possible in general relativity? Yes, they are, and some of them are quite curious. While most of space-time seems to be flat or gently rolling contours, physicists are aware of space-time regions with unusual and severe topologies, such as rotating black holes. Black holes are entities that remain from the complete collapse of stars. Black holes are the triumph of gravity over all other forces and are predicted by a solution to Einstein's general relativity equations. When they rotate, the singularity of the black hole creates a ring or torus, which might be traversable unlike the static black hole, whose singularity would be an impenetrable point. If an intrepid astronaut were to position herself near the horizon of the rapidly spinning center of a black hole, she would be treated to a most remarkable form of time travel. In a brief period of her personal time, she would witness an immensely long time span in the universe beyond the black hole horizon. Her space-time region would be so far removed from the external time of the surrounding cosmos that she conceivably could witness thousands, millions, or billions of years elapse. This is a kind of natural time travel. However, it severely restricts the activity of the astronaut, and she is limited to travel into the future. Are there solutions to general relativity that allow natural time travel into the past? Yes, but unlike rotating black holes, they remain only theoretical possibilities. Einstein's neighbor in Princeton, Kurt Gödel, developed one such solution. In 1949, Gödel discovered that some world lines in closed space-time could curve so severely that they curve back onto themselves, forming a loop in space-time. These loops are known as closed time-like curves, CTCs. If you were an object on a CTC world line, you would eventually arrive at the same space-time position from which you started. That is, your older self would appear at one of its own earlier space-time points. Gödel's CTC space-time describes a rotating universe. Thus, it is an extreme case for a CTC because it is globally intrinsic to the structure of the universe. It is not considered a realistic solution since current cosmological theory states that the universe is expanding, not rotating. One type of space-time region that a natural time traveler might exploit is a wormhole, two black holes whose throats are linked by a tunnel. Wormholes would connect two regions of space and two regions of time as well. Physicist Kip Thorne speculated that if one could trap one of the black holes that comprise the mouths of the wormhole, it would be conceivable to transport it, preferably at speeds near the speed of light. The moving black hole would age more slowly than the stationary black hole at the other end of the wormhole because of time dilation. Eventually, the two black holes would become unsynchronized and exist in different external times. The natural time traveler could then enter the stationary black hole and emerge from the wormhole some years earlier than when he departed. Unfortunately for our time traveler, if wormholes exist naturally, many scientists think that they are probably quite unstable. So any natural wormhole would require augmentation from exotic phenomena like negative energy in order to be useful as a time machine. Another type of CTC suggested by Gott employs two infinitely long and very fast-moving cosmic strings of extremely dense material. The atom-width strings would have to travel parallel to one another in opposite directions. As they rush past one another, they would create severely curved space-time, such that space-time curved back on itself. The natural time traveler would be prepared to exploit these conditions at just the right moment and fly her spaceship around the two strings. If executed properly, she would return to her starting point in space, but at an earlier time. One common feature of all CTCs, whether it is the global Gödelian rotating universe or the local regions of rolled-up space-time around a wormhole or cosmic strings, is that they are solutions to general relativity that would describe CTCs as already built into the universe. The natural time traveler would have to seek out these structures through ordinary travel and then exploit them. So far, we are not aware of any solution to general relativity that describes the evolution of a CTC in a space-time region where time travel had not been possible previously. However, it is usually assumed that there are such solutions to the equations. These solutions would entail particular physical constraints. One constraint would be the creation of a singularity in a finite region of space-time. To enter the region where time travel might be possible, one would have to cross the Cauchy horizon, the hourglass-shaped boundary of the singularity in which the laws of physics are unknown. Were such a CTC constructed, a second constraint would limit the external time that would be accessible to the time traveler. You could not travel to a time prior to the inception date of the CTC. Natural time travel, according to general relativity, faces daunting technological challenges, especially if you want to have some control over the trajectory of your world line. One problem already mentioned is that of stability, but equally imposing is the problem of energy. Fantastic amounts of exotic matter or structures and conditions similar to the early moments of the Big Bang, like membranes with negative tension boundary layers, or gravitational vacuum polarization would be needed to construct and manage a usable wormhole, infinitely long tubes of hyperdense matter would be needed for cosmic strings. Despite these technological challenges, it should be pointed out that the possibility of natural time travel into the past is consistent with general relativity. But Hawking and other physicists recognize another problem with actual time travel into the past along CTCs, maintaining a physically consistent history within causal loops. One advantage of some interpretations of relativistic quantum theory is that the logical requirement for a consistent history in a time travel story is seemingly avoided by postulating alternative histories instead of one history of the universe. Certain aspects of quantum theory are relevant to time travel, in particular the field of quantum gravity. The fundamental forces of nature, strong nuclear force, electromagnetic force, weak nuclear force, and gravitation have relativistic quantum descriptions. However, attempts to incorporate gravity in quantum theory have been unsuccessful to date. On the current standard model of the atom, all forces are carried by virtual particles called gauge bosons. A physicist might say that the photon carries electromagnetic force between real particles. The graviton, which has eluded attempts to detect it, carries gravity. This particle characterization of gravity in quantum theory. Thank you for watching. Please hit like and subscribe. I'm Paul, and have a good day.